Evening, everyone. Hi, guys. I've spun everything around tonight, hopefully to give us a bit better with the camera. I wasn't very impressed with last night, to be honest. So spun it around. Hopefully we'll get a better quick picture tonight. I've got some more notes to go through. I was going to aim to do probably about half an hour again tonight. So we'll do 15 minutes for, no, I don't know who even knows, to be honest. But we'll try and get some of the triple award stuff in, because I know some of you are here for your triple award exams as well as your double science. If you know anybody, obviously, who you think would benefit, feel free to share this sort of link with them and stuff like that. So see if we can get people involved. Shout out questions as they come up. If you want me to stop and go back and do something again, let me know. Remember that this is going to stay up on YouTube until, well, probably forever, because then the year 10s can use it next year. So you can always go back and look at it again if there's a bit that you think you've missed, or if there's something you want me to follow up. I'll try and do another one tomorrow night as well. So find me, send me some. Yes, I can go over electromagnetic waves. It's not a problem at all. That was part of what I planned to do tonight anyway. I was also planning on doing, for the triple awards, we'll look at some earthquakes very quickly, because there's not much to do in terms of content. That's very skills driven. I was going to do a little bit on thermal physics. I was going to do a little bit on, I can't remember what else, to be honest. A little bit on changing of state, things like that. So yeah, we'll get started if everyone's about ready. So we'll just do a quick recap of some of the things we talked about last night. I think that's nice. It sort of brings everybody who's seen that in with us tonight. So to remind you again of the national grid, I'll take my screen down again a bit. So our national grid, remember, this is our nice simple diagram. It can summarize the whole lot. So we've got power stations at the beginning, consumers at the end. Name some consumers: you, shops, houses, hospitals. The two important bits that score the big marks here are the transformers. So step up, step down transformers. Okay, so up, down. And they are increasing the voltage to decrease the current. Decreasing the current will reduce the energy loss by heat in the wires. Okay, it's a nice simple thing to try and remember. So step up, reduce the current, reduce the energy loss. Okay, and then we come down the other side, because that will improve the safety in the home. It will also make the electricity a little bit more usable. There are loads of power stations out there. We've got wind turbines, we've got nuclear power stations, we've got biomass generators, we've got gas power stations, a whole range, a whole mixture of different ways we can get our electricity. And that's really important, because like today, it's been very windy, so there's lots of wind energy available. Tomorrow, I think it's going to be a much nicer day, so there won't be quite as much wind around, so we'll need to use different power stations in order to get the energy that we need for our lives in the UK. So a variety of supply gives us security. It also allows us, sometimes the price of gas goes up, so we will try and generate using other means if gas is expensive, and that helps us at this end with lower electricity bills and stuff, okay? The national grid, remember, is doing more than just making sure electricity gets to your home through the wires. They're also watching TV with you to make sure that when you get up from the TV, there's electricity for the kettle to work. They make sure that we're not wasting it as well. So when we have more electricity than we need, they'll turn off power stations as well. They do a little extra thing. I didn't mention this last night. They will actually buy electricity in from places like Holland, Ireland, France. They'll sell electricity to those places as well, because it's unlikely that everywhere will experience a high demand at the same time. So we're able to just balance each other. So there's a bit of a sharing agreement that goes on. Makes a little bit of money for the national grid as well, I think. Okay, so remember, lots of different power stations to give us diversity. Step up transformers to increase the voltage, reduce the current, reduce energy loss. Step down transformers to make the electricity more useful and safer at the end. Okay, so that's national grid. Park that one for now. Watch out, of course, they're probably not going to get you to do a really nice, straightforward, easy question. They'll ask you something a little bit bizarre. They might show you a graph of energy demand throughout the day and ask you to talk about what's going on. They might ask you how the national grid would respond at 7 o'clock in the morning, and you have to look at the graph and see what's happening to the demand. And that's where you're going to show your knowledge by saying, well, the demand is low, so the national grid will reduce the supply of electricity by turning off a power station. Something like that. So obviously, read the question. They're probably going to want you to do a little bit more, though, than just like recite some stuff. Want to do the ring main for you? Yeah, I can do the ring main a little bit later on. That's not a problem. I've not got a diagram for that, though. So if we've got time, I'll try and do it on the end. Otherwise, I will make sure that goes into tomorrow's. Okay, that's not a problem at all. Right, so we'll do some quick tests. Okay, so test yourself as we go along. This is the standard circuit. This is probably the one that you're going to get. Yeah, okay, I can do energy transfers like that. Should be able to get those in tonight. So, ammeter, A in a circle, it's got to be a capital A, otherwise it's a waste of a mark. This cross in a circle, that's your bulb. Voltmeter, variable resistor. This rectangle is a resistor. The line through it makes it a variable resistor. This is a battery at the top. It's 2 cells making battery. We've got a voltmeter hiding under my hand down here. Diode, that allows current to flow through one way, only ever positive. We've got a different sort of variable resistor here. Notice the rectangle again. This is a thermistor. And there's one other that I've not drawn on here, but you might need to just be aware of what it is. That's a light-dependent resistor. Light-dependent resistors, their resistance goes down as it's brighter. They're really useful for controlling the sensitivity of your camera in your iPhone or your smartphone, whatever. Okay, so circuit symbols, remember the setup. The voltmeter always goes here. The voltmeter, it likes a hug, okay? If you're trying to find out something about the bulb, the voltmeter gives it a hug, it goes round. The ammeter, it stands off to one side, it maintains its personal space. But the voltmeter, he likes a good hug, so he comes across the component you're testing. And it could be anything. If it was voltage across this, you'd put it across, so you'd draw it around it like that. That's really bad drawing. Okay, so around it for the hug. Okay. Is that the HDR thing on a camera? No, it's slightly different to the HDR thing, but it's why when you're using your phone at night or you're using a laptop at night, the screen goes dim. Or you might find if you walk from a very bright outside into the house, all of a sudden the screen dims quite quickly. That's the camera responding. Yes, the ammeter can go anywhere as long as it's in series with the thing you're testing. So it's got to be before it or after it or on the same loop. You see how I've got a separate loop for the voltmeter? The ammeter is kind of in the same loop. Keep it close. That would be my advice, and make sure it's on the same loop of wire. Okay, don't put it on an extra loop. Okay, you probably get 1 mark for doing this, and you'll get 1 mark for doing this. So there's 2 marks in your exam there if that question comes up. Okay, you usually only need 1 ammeter, to be honest, because if we have 2 ammeters in the circuit, they'll probably tell us exactly the same thing. That's a question they quite like. They'll ask you to calculate the current in one place, and then ask you what the other ammeter must read. On a loop like this, if I had an ammeter here and an ammeter over here, they will both read the same because the flow of electric current through the circuit is the same in all positions. The voltage is across, but the current is through. So if I was to measure the voltage across the variable resistor, that would be a little bit more complicated. It would be a share of what's going on. But that's starting to get a little bit more tricky, so we'll leave that alone for now. Yeah, we can get away with usually only having the 1. Yes, we can go over Ohm's Law. That is the next thing on the sheet. Okay, so Ohm's Law is this thing here, and it relies on the fact that current and voltage are proportional to each other if the temperature remains constant. So I've got some little graphs. Here we go. So I'll talk you through these again from yesterday. We'll ignore this horrible one for now. It's nasty. I'll try and sort myself out. So this one over here. So this is an ohmic conductor. So this, Grace, is something that follows Ohm's law. So as you can see, current and voltage give us a straight line on this thing. And here, mathematically, anything that goes through 0 and has a straight line, we can call directly proportional. So Ohm's law is that current and voltage are directly proportional to each other. Okay. Other side of the page. So this is a filament light bulb, a bit like one of those old light bulbs, or maybe like a flash bulb from a camera, maybe. The old school light bulb, that one is, it changes temperature as the current flows through it. So as I increase the voltage, I get more current, but as I get more current, I get more resistance. And as I get more resistance, I get more heat. And that increases the resistance. So it curves until we reach a point where I can increase the voltage, but I don't get any increase in current at all to go with it. Now, just so that you've seen it, because sometimes the exam board draw it that way, they quite possibly will give you a graph that looks like that. Okay, I'll hold them a bit closer so you can see them. You can see the clear difference, this one being straight and this one being curved. So that's all you really need. But just in case, the exam board might give you this. And what they're interested in is the fact that you know that it's the same backwards. If I take the battery out and turn it round, so the current flows the other way through the circuit and the voltage is the other way around, it's the same pattern on both sides. It's like there's a mirror reflecting the two sides. Okay, so this one is non-ohmic because it's not a straight line. This one is an ohmic. Constant resistance, increasing resistance as the voltage is increased. Okay. When it goes negative, is that the maximum output? No, I think you've got something a little bit mixed up there, Brett. Okay, so the maximum power of this bulb would be up here because power is current times voltage. So maybe the exam board would give you a graph. They'll ask you to do something with it. I don't know, and they might say, what is the power output of the bulb at 2 volts? And what you would do is you would read up from 2 on the graph, and then you'd measure the current, and you'd use those two numbers to calculate the power, okay? Just be aware that, one last thing on these, the gradient, so the steepness of the line is opposite to resistance. So as it's steep here, that's very low resistance, not so steep, high resistance, okay? And then lastly, I've got one more of these, and that's for the diode. The diode, remember, only allows current to flow through one way. So here's its little graph. It does something a bit funny. It's a bit lazy. You've got to give it a bit of a push. But once you've started, once you're past 0, this is at about 1 volt, I don't know, it will increase in a nice straight line. So diodes become ohmic conductors after a certain voltage has been applied, okay? If we had a negative axis on this, I should have drawn it in the middle of the page so I could have come back. But if we had a negative axis, it would be flat. There would be no, it wouldn't be like the filament light bulb. It wouldn't come down like this. It would just stay on the level. They don't allow any current to flow through them the wrong way, okay? So ohmic conductors, resistors, or metal wires, filament light bulbs, they get hot. So they are non-ohmic because the temperature is changing and you have a curve on the graph. And then diodes have a funny sort of kickoff point and they have no current for negative voltages, okay? Right, I was going to do another quick recap of the electromagnetics like I did yesterday. So remember, here's your list. Both of our physics classrooms, I think, have got the posters on the wall, and we always put them up in the right order. So you've got radio waves at one end, and you've got gamma waves at the other. So try and remember them in order. So radio, micro, infrared, visible, ultraviolet, X-rays, and gamma rays. Radio wave have the longest, that's the longest name, isn't it? Longest wavelength. Gamma, that's the shortest one. Oh, gamma is the shortest one, so they're the shortest waves. Highest frequency, because they're opposite. So high frequency, low frequency. Low energy, high energy. Okay, so everything's on a scale. And then visible light, the stuff we see, that's arranged in the middle. It's about halfway through. Now, there was something special, if you remember, about ultraviolet X-rays and gamma rays. These are high energy because they're down at this end, highest, but all of them are high. They are dangerously high. They are what we would refer to as ionizing. That means that they can change the properties of materials. So they can knock electrons off atoms, leaving ions. You know about ions from chemistry. That can change the way that things behave, and that can have really profound effects on biological entities like our cells. So they start damaging our cell membranes. They start breaking bits of our body cells. They start preventing organs from working properly that way. But also, they can actually change our DNA. So they can break bits of DNA, causing the cells to die, or they can cause mutations to the DNA, which then get passed on. And some of those mutations can be cancerous. So we need to be very careful around ionizing radiation. So high energy means they're ionizing. Ionizing can damage, kill, mutate cells, leading to cancer. Okay, that comes up quite often. All of these are radiations. So I don't want to say that the bottom three are radioactive. I want to say that these are all radiation. They're electromagnetic radiation. I want to say that these are ionizing radiation. And next year, I'll teach you about nuclear radiation, which is also ionizing. That's probably where you're getting the term radioactive from, but leave that alone for another couple of months, okay? High energy, ionizing, cancer. Right, so I've then got some extra stuff. So this is a little bit triply. Okay, so if you're a double student and you just want to just chill out for a moment, keep an ear out for what's going on, I've drawn this graph for the triple award, guys. Just tilt it down a little bit because I'm starting to get cramp in my fingers. So if we draw a graph, so this maybe could be ice. Okay, so ice down here. I'm going to put ice in a beaker and I'm going to gently heat it with a Bunsen burner. And what will happen is the temperature of the ice will go up as I put energy in. Okay, nice, easy one. You know about that, not a problem. And then something funny will start to happen. The ice in the beaker will start to melt and the temperature will stop rising. The energy being supplied by the Bunsen burner instead breaks the bonds between the ice molecules. Yeah, Abby, I can have a look at magnetic fields. That might need to go into Thursdays, if that's okay, but I'll try if we get time. So as we supply more energy here, we're breaking the bonds between the molecules, and that means the temperature doesn't go up. As soon as the last bond is broken, up goes the temperature again, because once again, energy being supplied increases the temperature of the water now. So we started as ice, we now got water. And then you can see here, I've just about managed to squeeze it on. Here, we've got another flat section on the graph. So more bonds must be being broken because the temperature isn't increasing. This time it's the bonds between the water molecules and off they go to become steam. And then if we carried on, we'd see the graph rise again at the end as the temperature of the steam starts to go up once all of the bonds holding it in its water form have been broken. Okay, so that is a pretty standard graph. We had a lovely 6-mark question on that last year, quite well answered. It's something that you guys either get or don't get. So just remember, if you're having that I don't get this moment, the temperature increases because energy is being supplied. Here, the temperature doesn't increase because the bonds are being broken. All the bonds are now broken, so energy being supplied causes another raise in temperature, and then again and again, right? So it keeps on. If we were to do the opposite, we could actually draw the graph the other way around. We could talk about putting ice cubes in the freezer, putting water in the freezer, and we'd have exactly the same graph, but it would be the opposite way around. It would be reflected, okay? And on the back of that, I think I've written down some... No, I haven't actually. So to go with that, there's 2 equations on page 2. There's specific heat capacity and there's specific latent heat, which is similar but slightly different. So if we wanted to know how much the temperature would change for the amount of energy provided, we can do a little bit of maths. So they will give you some data. The formula is all ready for you on page 2. And with that data, you need a mass. You need to know the specific heat capacity of water, which will be given to you. Sorry, water, whatever it is you're doing. You'll be given the specific heat capacity, you'll be given the mass. you can then calculate a temperature change from that. Okay, so it's nice easy maths really, because it tends to be just timesing lots of stuff together. Specific latent heat, that's the amount of energy that's supplied to cause this breaking of bonds down here. Freya, when you get a chance, if you go back to the beginning, I did a bit on the national grid right at the start. Okay, if I get a chance, I will nip back and we'll do a quick recap though. Here, again, you'll be looking at data and you'll be looking at the formula from within the exam book. And here, this one's a little bit easier because there's one less thing. You need to know the latent heat, it's called, and the mass of the stuff that you've got. Okay, so again, find the formula, use the information provided, reasonably simple calculations to do with that one. Okay, I've made some more notes on that bit in particular and put them onto Instagram today. So if you can grab those, that's just boring physics again. There's kind of a theme going on here, guys. While we're on the thermal, I've got this for, again, triple awarders. Are you guys talking to each other like in separate rooms at the moment? So pressure, volume, and temperature are really, they're linked together really strongly. So if I change the pressure of something, I have to either change the volume or the temperature to keep it constant, right? Now, if I take I don't know, the gas inside a balloon, okay? If I was to work out the pressure inside the balloon, the volume of the balloon, and the temperature of the air, times those two together, divide it by that temperature, I'd get a number here. Now, if I was to take that balloon and put it in the fridge so that the temperature goes down, this number that I calculated, the constant value, has to stay the same. So if temperature goes down, one of these two numbers must go up. And what would happen for the balloon is that the volume of the balloon would shrink. You know, when you leave a balloon alone, it goes a bit wrinkly, so the balloon would shrink down a bit. Okay, now if I do the opposite, if I take the same balloon out, let it warm up again, it will come back to where it was. If I put it now in the oven, so the temperature rises, still has to be equal to the constant value. So the pressure in the balloon must stay the same because it's to do with air pressure. The volume of the balloon must increase. So you see the balloon expand. And you've probably got some experience with this. You might have noticed crisp packets changing size. On cold days, they seem quite small and on, empty of crisps. But on a hot day, they're all big and fluffy. You might have come across quite a few examples of this. If you've ever used a bicycle pump, you might have noticed as you squeeze the bicycle pump, the actual pump itself gets hot. And that's because the gas is trying to lose temperature because you're trying to maintain this constant state that it's in. Okay, so I'll leave thermal there for tonight. I can do a little bit more on that in a couple of days. Oh, sorry, tomorrow if people want. And then I think that was the last thing that I had planned in, apart from the triple awarders, some earthquake stuff. So this is a seismometer trace. The seismometer trace, it shows us, it's made by the wiggly pen. So if you imagine that the pen is moving across the paper, or perhaps better actually, the pen stays still and the paper moves underneath it. If the pen, or if the paper is moving and the earth underneath the paper moves around, it's going to leave a funny little pattern on the paper as the pen moves across. Okay. So I've got station A. So these are very simple to do. You take this pen setup I'm talking about, you glue it to the ground, and if the ground moves, it makes a funny mark on the paper. So station A has picked up an earthquake here. So the first waves to arrive are P waves. Per for primary, they arrive first. The second waves, S waves, secondary waves, arrive second. There you go. Who knows, right? And you will be given probably in your exam paper, Connor, probably not. These aren't going to be in, I don't think. If you're the right Connor anyway. I can try. It's difficult on that one though. Right, so these two here are separated by something called a lag time. If you take these two times, we can then take them away from each other to work out the lag time. The lag time will tell us how far away the earthquake is. So I know from measuring the lag time how far away it is from station A. I know from looking at the second one here, I've got another lag time. See how this one is bigger? The earthquake must be further away from station B. If I know how far it is away, I can draw a little map. I can draw little circles that cross over. I need another one though. I need a third station, and that will tell me exactly where the epicenter of those three circles meets. X marks the spot. There's the epicenter. They do quite like that. There's a relatively simple 1 or 2 marks on that. Okay. So a couple of requests coming in. So can I go through voltage? Right. Okay. Voltage is used badly as a term in schools and out there in life. Voltage means, even bits of paper everywhere. Voltage is the measurement of potential difference. Potential difference is a property of reacting chemicals or other situations. And a battery, for example, there is a difference between the two ends. And when you connect something like a light bulb between the two ends of a battery, you're going to experience, or the electrons in the circuit are going to experience the difference in potential. How do I measure that? With a voltmeter or a potentiometer, a voltmeter, and that's going to measure me 1.5 volts. So voltage is the unit for measuring potential difference, okay? It's kind of the energy, well, it is the energy being carried by the charges. So if we want to know the total amount of energy transferred, we can do the potential difference, that's in volts, times the current, times the amount of time that it's been happening for, okay? So we can do some calculations using that. It's a measure of energy being carried by the charges in a circuit, okay? Right. Can I do the coil stuff? Right, yeah, I can. Let me just do a little bit of drawing while we're talking. So transformers obviously are really important for you studying the national grid, but you don't need to know how they work. You just need to know that the step up increases voltage to reduce current, and that reduces energy loss. Now, the triple awarders, you need to know a little bit more. So you need to know that, if I tell you what, let's do a little bit of talking first. So if I take a magnet and move it inside a coil of wire, the magnetic field changes because the magnet's moving, right? The changing magnetic field inside the coil of wires, I'm trying to do a coil, right? So we'll spin it like this, right? So if we change the magnetic field inside the coil of wires, we are going to get a current produced, okay? And as the north pole goes past, it's going to push the current one way. And as the south pole, because I'm spinning it, as the south pole comes past, it's going to push the current in the other direction. So I'll end up with something that looks a bit like this. So as the north pole goes past, I'm going to have a positive, and then as the south pole goes past, a negative, and then a positive. And this is AC electricity, okay? So alternating current. That's where it comes from. And if I have more coils, I'm going to get more current. If I have more speed, if I spin it faster, I'm going to get more. If I have a bigger magnet, I'm going to get more. So there's some simple, you won't have to do any maths on that, not until you get to year 13, but there'll be a little bit of maybe qualitative, where you say, get a bigger magnet, get more coils, that sort of thing. Just watch out for that. Now, we can use this for transformers because we said it was a changing magnetic field. So if I've got 2 coils of wire, if I put AC electricity through this, the moving current will make a magnetic field. And as the alternating current moves backwards and forwards, as it flips around, it will flip the magnetic field up and down inside this coil. This is the primary coil. And as the magnetic field flips around here, because magnetic fields don't stay where you put them, they sort of leak out, there's a magnetic field over here as well. And from here, so this one will flip around as well. So as the current flows through here and makes a magnetic field on this side, we get a similar matching flipping magnetic field. And if I change, remember, the magnetic field inside a coil, I'm going to get a voltage, I'm going to get a current flowing on this side as well. So this one, I think, if I've drawn it, yeah, I have. So I've got 1, 2, 3 coils on this side, I've got 1, 2, 3 coils on this side. So the same amount of magnetic field on both sides, same number of coils, I'm going to have the same amount of voltage. We would call this an isolating transformer. This is how my electric toothbrush charges, because I can plug it in, because I don't want electricity in my bathroom. It's a dangerous place to have it. Yes, left hand, right hand, do that tomorrow. So on this side here, we get the same out, but no electricity had to flow. There's no chance I can electrocute myself in the bathroom. So that's isolating, where you have the same number of coils on both sides. Now, the next example is if we put loads of coils on the secondary. I'll just draw some extra coils in, if only it was that easy. Okay, so now I've got more coils on the secondary. So I don't know, let's put 10 volts in here. If I've got 4 times as many on this side, I'm going to have 4 times as much voltage. So this is a step-up transformer. If I turn it the other way, look at that, genius. Right, so now on my primary coil, I've got 4 times more on the primary than I have on the secondary. This time, when the voltage is created on this side, it will be 4 times less because I've got 4 times less coils, okay? So keep an eye out for that. There's a really complicated, nasty looking formula. It says something like N1 over N2 equals V1 over V2, whatever it is. So you can find that on page 2 if you need to do any maths. But it's a ratio game. If you've got double the coils, double the voltage. Okay, so watch out for that. At the same time, though, just be mindful, and you know this about the current from the work on the national grid. If the voltage has gone up 2 times, the current must go down by 2 times. So step-up transformer is for voltage, and at the same time it's stepping down. I don't want to say that out loud though. It's reducing the current by exactly the same proportion. So keep an eye out for that. There's some nice easy marks, I hope, to gather on an exam paper from there. Okay, so that's our half an hour for tonight. I don't want to overload anybody or myself, if I'm honest. I've got a list of things. I'll keep hold of this list that I will go through tomorrow. We'll do a little bit more on motors for the triple, because I've not done anything on those yet. And then we'll go back. We'll hit what I think are the most important issues here. We'll talk a little bit about fossil fuels, different ways we can generate some power stations. We'll hit again that national grid, because that is going to be on there, right? You can't get away from it. We'll do the ring main as well. We'll have another quick chat about electromagnetic radiation, and keep going with the comments. Comment on the video as well if you watch it later on. Stick some comments on there if there's anything you want tomorrow. All right. So you're welcome, guys. It's been an absolute pleasure. Like it, share it, make sure people know that it's there, because the thing that I worry about most is that I'm doing this, we're putting the effort in here, because you suggesting things is helping other people as well, and other people don't know it's here. So let everyone know, okay? Do you just want... No. Why would I want to do that, Lucas? You must be mad. And with that, I'll say good night. Get some rest, guys, and I'll see you all in school tomorrow. Okay? Bye for now.